Hi, and welcome to RadOnc Talks, a lecture series designed for students and residents of radiation oncology. My name is Ria Mulherker. I am currently a fourth-year radiation oncology resident at the University of Pittsburgh, and today I will be taking you through our final installment in the Introduction to Radiation Oncology series with an introduction to radiation physics. Physics was probably the number one subject that overwhelmed and intimidated me as a medical student starting out my RadOnc journey. And so if you're a little bit scared to dig deeper into this topic, it's completely understood. We have all been there. I do want to reassure you, there is a lot of physics in radiation oncology, yes, but the actual physics that we use on a day-to-day basis is still fairly minimal. And we rely heavily on our physicists to do the actual math and calculations that relate to our plans. As radiation oncologists, we are still physicians, and that is our primary job. However, it is very important for us to understand the physics of what is happening when radiation hits the patient, the physics of how our radiation treatment machines work, and so it's important for us to invest a lot of time and understand this subject. But once you put that time in and once you understand what is happening to the patient, the day-to-day becomes very simple and it's actually super interesting. So what I'd like to do in today's talk is to first hit on photon interactions with matter. So kind of understanding what happens when radiation hits the body. And then secondly, we'll talk about generating photons. So how do our linear accelerator treatment machines actually work? And kind of understanding how radiation is delivered. If you watched any of our prior introductory lectures, you know by now that the primary modality that we use in radiation is external beam radiation, which involves photon treatment delivered via a linear accelerator machine. And so that is why in this introduction to physics, we are primarily focusing on what happens when photons interact with matter. There are other modalities, there's electrons, there's protons, and so on. But the bread and butter of radiation really involves using photon treatment with a linear accelerator. And so that's why we're focusing just on photons for now. So just to review, what is a photon? We know that a photon is a massless packet of energy that moves at the speed of light. Photons are thought of as both particles and waves that exist on this electromagnetic spectrum. So they have both particle-like behavior as well as a wave-like behavior. And we know that the electromagnetic spectrum shown here ranges all the way from radio waves up to X-rays and gamma rays. At the lower end of the spectrum, the lower energy end of the spectrum, the wavelengths are long. And then at the higher energy end of the spectrum, where the frequency is high, the wavelengths are very short. And it is at that higher end of that energy spectrum where we have X-rays and gamma rays. And these are the types of radiation that represent ionizing radiation. So going back to our introduction to radiation biology lecture, ionizing radiation is radiation that is capable of causing an electron to eject from that outer shell of an atom's orbit and creating ionized atoms. So X-rays and gamma rays are both photons. They're massless packets of energy, and they represent ionizing radiation. There are four main interactions that can happen when a photon hits matter. These are coherent scattering, photoelectric effect, Compton effect, and pair production. If that sounds like a foreign language to you right now, do not worry. We will go through each of them one at a time and understand. What I want you to understand right now is that any one of these interactions could be happening at a given time. However, what we're interested in is the probability of a particular interaction happening. And as you will see, the probability of one of these happening varies largely depending on the energy of the incident photon, as well as the properties of the absorbing material itself. And some of these are more likely at the energies we use to treat radiation, and some of them are not likely at all. The first interaction that we learn about is coherent scattering. Coherent scattering occurs at very low energies. It applies to low energy photons, much lower than what we would use for diagnostic or therapeutic radiation. In order for a photon to have an interaction with an electron and release the electron or cause something to happen to the electron, the photon has to have a higher energy than that resting electron in the orbital shell. In coherent scattering, what we have is an elastic scattering event because no energy is lost by the photon. Why? Because the photon doesn't even have enough energy to overcome the resting energy of that electron. So I think of it as just bouncing off the electron. And there are two types. There's Rayleigh scattering and Thomson scattering. In Rayleigh scattering, it's elastic scattering by all of the electrons in the atom. So think Rayleigh all A scattering. And then in Thomson scattering, it's elastic scattering just by one electron in the atom. So think Thomson 1. The probability of coherent scattering is proportional to Z, so the atomic number, divided by the energy squared. You can tell by this formula that as the energy increases, the probability of coherent scattering greatly decreases, right? Because in the denominator we have energy squared. So as energy increases, the probability of this drastically decreases. So just remember, coherent scattering is an elastic scattering where no energy is lost by the photon, and it happens because the photon energy is too low to do anything to these electrons. The next type of interaction is called the photoelectric effect. And this is actually relevant to us because this effect predominates at certain levels that might be used in diagnostic radiology. In the photoelectric effect, our photons are at energy levels that are high enough to cause ejection of an inner shell electron. Remember, electrons are arranged in concentric shells around an atom, and the lower energy shells are on the inside closest to the nucleus, whereas the higher energy shells are on the outside furthest away from the nucleus. So in this case, the photon has an energy that's slightly higher, high enough that it causes ejection of an inner shell electron. At this point, an outer shell electron that's of higher energy will lose some energy and come to this lower energy shell and kind of fill in the place. I think of this as if you have an auditorium or a classroom and one of the front row seats opens up, then somebody from the back will come in and fill in that front row seat. In the process, that higher energy shell electron releases some energy, and that release of energy is called a characteristic X-ray because a photon is released. If that photon goes and hits another outer shell electron, there can be something called an Auger electron, which is expelled as well, and we will talk about all of this with some diagrams. But for now, just understand that photoelectric effect is slightly higher energy photon causing ejection of an inner shell electron. In the process, a characteristic X-ray is released. There is something known as a resonance phenomenon where photons that have an energy closest to the binding energy of an inner shell electron are more likely to result in the photoelectric effect, which makes sense because, you need to have an energy that's close to that of a binding energy electron. The other thing to note is that the probability of this interaction occurring is proportional to the density represented by rho times Z cubed divided by E cubed. So this interaction depends very, very heavily on the atomic number. So here's a diagram to kind of visually explain what is going on. So in the diagram, we have a nucleus in the center, and then we have the K, L, and M shells kind of concentrically arranged around the nucleus. So the incident photon will hit an electron in the K shell, which is the lowest energy, and that electron will be released because the photon has a high enough energy to release the K shell electron. Now that a front row seat is opened up, an electron from the next shell, the L shell, will kind of fill in the place of the electron that flew away. In that process, when the electron goes from the L to the K shell, a characteristic X-ray is released. So this characteristic X-ray has an energy that represents the difference between the L and the K shells. And that's why it's called characteristic, because that energy will never change. That's always going to be the same quantized amount. So it's called a characteristic X-ray, and that amount of energy is released. Now, if that characteristic X-ray is released and it happens to have enough energy to release another electron, such as the M shell electron in the diagram on the right, that next electron that's released is called an Auger electron. So an Auger electron may or may not be produced, but a characteristic X-ray is always produced. Now, we talked about this phenomenon of resonance, but basically resonance means that photons with an energy that are closest to the binding energy electron are more likely to result in the photoelectric effect. So if we're looking at a probability curve of a particular reaction happening, the curve has peaks that correspond to the energy of those respective shells. So resonance peaks are named for their electron shells. So if a particular peak has a higher probability of displacing a K electron, that's called a K edge. So these peaks are actually exploited for their use in imaging contrast for diagnostic imaging. And the reason that the photoelectric effect is really good for diagnostic imaging is because, remember how it's proportional to rho times z cubed over e cubed? Well, that z cubed leads to a huge difference in contrast for something like bone, which has a much higher Z material, compared to soft tissue. So that was resonance. The other important thing to realize relating to the photoelectric effect is the production of these characteristic X-rays. So characteristic X-rays are emitted as outer shell electrons decay to a lower energy inner shell. And in the process of going from a higher energy to a lower energy, they have to lose some energy, which represents the difference between those shells. So when characteristic X-rays are released, the energy in those X-rays is tied to quantized energy levels between the electron orbitals. And that quantized energy is unique to a particular given element and whatever that difference is between those two shells for that element. So all of that was photoelectric effect, and hopefully that made some sense. The next interaction we're going to talk about is what is known as Compton effect or Compton scatter. And this is where the money is. This is the most prevalent interaction that takes place at therapeutic levels of radiation. It can also happen at diagnostic levels. This is the most probable interaction that happens in water from energies ranging from 30 kiloelectron volts to 24 mega electron volts. So there's a wide range there. But this is the main interaction that happens in therapeutic levels of radiation. So this is what you really need to understand. And this is what I imagine is happening inside of patients when radiation hits them. So in Compton effect, we are now talking about photons that have a higher energy than what they had for photoelectric effect. These photons have a high enough energy that when they hit an electron of an atom, the electron can actually be ejected from the outer shell, so the highest energy shell. And the incident photon still has some energy that's retained within it, so that incident photon gets scattered. So what we end up with is an incident photon strikes an outer shell electron. That electron is released, and the photon gets scattered. So depending on the energy of the photon and the energy of the electron that it hit, there is still some energy retained within the photon. And often there's enough energy to go and interact with another electron and cause the same thing to happen again until the photon continues to lose energy. If you recall from the radiation biology introductory lecture then, the ejected electron is the thing that can go and then directly or indirectly cause DNA damage. So release of these outer shell electrons is key because they can then build up, and once they build up to an effective enough level, they are the mediators of direct and indirect DNA damage. If you don't know what direct and indirect DNA damage are, I would recommend going to check out lecture 2 out of 3 in this intro series where we talk about Introduction to Radiation Biology. Without getting into too much more detail, one thing that you can realize about the angle at which that photon is scattered in Compton scattering, as the energy of the photon increases, you can imagine that it has more momentum to keep moving forward. So as the energy of the photon increases, the direction of the scatter is more forward peaked. And so, in 0 degree scatter, the photon loses no energy. It just goes straight through the electron. At 90 degree scatter, the photon can retain up to 0.511 mega electron volts, and 0.511 MeV is the resting mass of an electron. So at 90 degree scatter, the photon retains that. At 180 degree backscatter, the photon can retain up to 0.255 MeV. So just realize that as the energy of the photon increases, the direction of the scatter is more forward peaked. This brings us then to our last interaction that we need to realize, which is pair production. So pair production occurs at much higher energy levels, and it's actually typically not even a concern in radiation therapy for beam energies under 10 MV. So this happens at really high energy levels. And pair production occurs via interaction of a photon with an atomic nucleus. Technically, we need at least 1.022 MeV, which is twice the resting mass of an electron, which we said is 0.511 MeV. So a photon will go of a high enough energy, like a really high energy, will go and hit the nucleus, and it will cause creation of an electron and a positron. So it's essentially what it's doing is it's enough photon energy that hits the nucleus, and it's causing one of those particles to split into an electron and a positron. The probability of pair production is proportional to Z times the ln of the energy, so the natural log of the energy. And again, pair production we don't really deal with, but it's just something to be aware that can happen at really high energies, theoretically for beam energies above 10 MV. So take a deep breath. We made it through those 4 interactions, those 4 photon interactions with matter. And here we just have a quick summary listing those out, the probability of them happening and so on. What I really want you to take away is that the photoelectric effect and the Compton effect are the 2 most important interactions that we worry about in radiation. Photoelectric effect predominates at energies used in diagnostic radiology, and it's proportional to Z cubed, so it largely depends on density. In X-rays and in CT scans, there's always a huge contrast between the bone, which typically appears white, and then the soft tissue, which appears more gray. That's because the density of the bone is huge, right? It's made up of calcium, and the atomic number is much higher than that of the elements in soft tissue, which is predominantly made up of water. So that's how you can really remember that the photoelectric effect used in diagnostic radiology is proportional to Z cubed. The Compton effect, on the other hand, depends very little on the atomic number Z, and what's more important is the electron density. So hydrogen actually has the highest electron density, and other atoms are nearly all equal. So Compton effect doesn't differentiate as much based on the Z of the atomic material. It depends more on electron density. And this is the interaction that's really predominating at therapeutic radiation levels. And so when radiation hits a body and we're trying to treat somebody with radiation therapy, think of the photons interacting with the matter, causing a bunch of electrons to be released, and eventually there's enough electrons built up in the tissue that we actually start to see some DNA damage from those electrons. Here we have a quick little diagram showing the probability of each of these interactions occurring at different energy levels. So again, it's really important to realize that any one of these interactions could theoretically be happening at any given time, but the probability just changes depending on the energy level that we're dealing with, as well as the properties of the material itself. So let's move on now and switch gears a little, talking about how are photons actually generated. If you recall from prior lectures, photons are generated in a machine known as a linear accelerator, often called LINAC for short. So a LINAC utilizes microwave technology to accelerate electrons towards a heavy metal target, usually tungsten. And this process results in the creation of photons. So what's actually happening in the head of the machine where electrons are being accelerated towards a tungsten target, because it is a heavy metal nucleus, it's a heavy nucleus, there's an interaction known as the Brehmsstrahlung interaction, creating Brehmsstrahlung X-rays or breaking radiation. And this is how photons are actually generated and how the photons then exit the head of the machine. And these are the X-rays that we use to treat the patient. So Brehmsstrahlung was a big word. What does that exactly mean? So Brehmsstrahlung, or breaking radiation, is produced as a charged particle slows and scatters during interaction with an atomic nucleus. It's actually a pretty inefficient process. So within the linear accelerator, electrons are accelerated using this microwave technology like we talked about, and they hit this tungsten target. And because the nucleus of tungsten is so heavy, the electrons kind of are slowed by the interaction with the nucleus. The electron path is bent by the interaction, and that loss of energy is released in the form of photons. So there's a photon emission that happens. Like I said, it's a highly inefficient process, and the average energy of the X-ray beam that is released is actually just 1/3 to 1/2 of the maximum energy of those incoming electrons. But this is the process that's taking place in the linear accelerator machines, and this is how the photons that we use to treat patients are actually created. Now, in the head of the linear accelerator machine, so where the photons are coming out from, there are several components. First of all, like we talked about, we have a target, and that's usually a tungsten target, which when the electrons hit that target, it results in the release of photons. And there can often be different bending magnets and things like that, which we don't need to get into, but these essentially help to shape the direction of the photons coming out of the beam. Now, there are different components that are in the head of the gantry, and we don't need to memorize all of them at this moment. One of the things that may or may not be present is something known as a flattening filter. If a flattening filter is in place, it's usually to help create a more homogeneous beam. So if you look at a beam from one side to the other, there can often be some variation in the energies of the beam, depending on if it's in the center of the axis or more on the periphery. A flattening filter can actually help to create some homogeneity there. But at the same time, it can lower the rate of the dose of the beam exiting. So often in stereotactic radiation, when we're trying to deliver a much higher dose, in order to decrease the amount of treatment time, we may actually remove the flattening filter and accept a less homogeneous beam to help decrease that treatment time. That might be a little bit complex to understand at this level, but just realize that a flattening filter may or may not be there. The next component within the LINAC head that's super important to know about is the jaws and then the multi-leaf collimators, or MLCs. So these are tools that we use to help better shape our radiation beam and try to increase our conformality to a particular target volume. The jaws are probably, the most important thing to realize, because the jaws help us to define our field size. So let's say that at maximum, our treatment machine can treat a field size of 20 by 20 meter cm. So that means the maximum field that you might be able to treat is 20 by 20 cm. But let's say our target is smaller than that, and we actually want to treat something that's 10 by 10 centimeters, or maybe 8 centimeters by 10 centimeters. We want to create a smaller square or rectangle. We can draw in our jaws, and we have X jaws and Y jaws to kind of shape that square or rectangle to whatever smaller size we want. From there, we may want to actually decrease our field size a little bit further, but maybe we want to just decrease it in the top area and have it be wider in the bottom area. This is where the MLC leaves come in. And I think it helps to look at it from this beam's eye view perspective. So in this beam's eye view, we have the X jaws and the Y jaws, and they are coming in at different angles to create a square. From there, we have the MLC leaflets, and everything in green is what the MLC leaves are blocking, and everything in blue is where these openings are. So these MLC leaves come in and they help us to shape the beam, and often they can move dynamically during the treatment. So as the radiation beam is being delivered and the beam is being modulated, the MLCs can move in and out of the picture to help better increase conformality of our radiation beam to our target volume. So those were just some components of our LINAC head. Now, the other thing to realize is that the LINAC can be used both to treat with photons, but it can also actually be used to treat with electron therapy. If you recall from a prior lecture, electrons have a mass that's about 1/2000 that of a proton. So they're 2,000 times lighter than a proton. And because of that light mass, they're good for treating very superficial tumors because they don't penetrate very deeply through the body. In case of an electron, we still have the same mechanisms where electrons are accelerated towards a tungsten target, which results in the creation of photons. Once the photons start exiting from the head of the machine, though, within the head, we have a scattering foil in place that actually results in the production of electrons. So it's a little bit backwards if you think about it, because we make electrons, we hit them to a target, convert it into photons, and then we put another scattering foil to produce electrons. But that's kind of what we're doing. So we had a flattening filter shown in the prior situation for the photon beam homogeneity. This is not necessary anymore, and it's actually changed for a scattering foil to help us produce electrons. At the very bottom of the head, we actually apply something known as an electron applicator. You might hear the word cone. And the cone helps us to kind of shape the electrons to the target volume once again. So just to be aware of that, the same LINAC that's used to treat with photon therapy can actually be used to treat with electrons as well. But electrons are used for superficial targets. So up until now, we've really just been talking about the components in the LINAC head. And the head is just a part of the gantry. That's the part that the patient looks at, straight above them when they look up while they're getting radiation. That's the treatment head. The gantry refers to that entire large machine-like device that sticks out of the treatment rooms. That's what we see when we walk into a treatment room. The gantry itself can actually rotate around the patient and deliver radiation from a lot of different angles. In VMAT plans, for example, that volumetric arc therapy, the gantry moves in a continuous circle around the patient the whole time. So radiation is coming from all different angles while the gantry is rotating. Even if we're doing just, static IMRT or something like that, we can rotate the treatment couch in different positions. And, by rotating the treatment couch, by rotating the gantry itself around the patient, our radiation can then come into the patient at a lot of different angles. And these are things to think about when you're doing treatment plans. And sometimes you may want to avoid things, like you may want to come in at an angle that avoids going through a patient's arm. So it's just important to realize what tools we have and how we can use our machines to deliver the radiation appropriately. So we're almost done, I promise. But in these last few minutes, I just kind of want to bring together what we talked about in the first half of the lecture, how do photons interact with matter, and then now understanding how the machine is actually working, how we're angling the gantry so that the head is positioned exactly where we want it to. What is happening when the photon actually enters the patient? So just to kind of review, remember that it's the therapeutic energies that we're using for radiation. X-rays enter the patient, and the predominant interaction that's happening is the Compton effect. So ionizing radiation is causing electrons to be released from the outer shell of the atom's orbit, and these photons that hit the electron are getting scattered. They're going to interact with other electrons, releasing them from their shells, and what we're ending up with is a buildup of all these free roaming electrons that are free to cause some DNA damage. So if you realize now that when a photon hits a patient's tissue, it needs to have some interaction with that tissue to lead to the ejection of these electrons. And these electrons are actually the mediators of DNA damage. If you understand that, you'll understand this concept of percent depth dose. So when photons hit the patient's tissue, we know that they're not immediately effective. So they're not giving radiation necessarily at the surface of the skin, because they first need to interact with the tissue to create the electrons that mediate the damage. So it actually takes some time to build up to this maximum dose, because you can imagine when a photon hits, the tissue, some of those photons will immediately result in ejection of electrons, but some of those photons will penetrate a little bit deeper before the electrons are released. So as this process is happening, as the photons are hitting, as the electrons are being released, this process really takes place in those first few millimeters. And after a little bit of depth within the tissue, that's when we have kind of maximized the number of electrons floating around in the patient's body. That region, before we get to that maximum dose, it's called the buildup region. And then we eventually do reach that maximum dose, and that is known as Dmax. So that's the peak of the curve that we see. What we see on this slide is a graph where the effective dose is plotted against the depth inside of the patient. So in those first few millimeters to the first centimeter or so, we have a buildup region. Then we have a maximum dose, or the Dmax. And as more and more, electrons continue to be ejected, those photons keep scattering and they're losing their energy. After we get to that Dmax region, the effective beam attenuation takes over. So those photons start to get scattered and we start to see less and less electrons released from the orbits. So, initially when a photon hits the patient's body, it's not quite at its maximum therapeutic dose. First, there's a buildup region, then we reach Dmax, and then as those photons keep getting scattered and losing energy, we have an effect known as attenuation, where the photon beam loses energy as it moves through the body. And again, this entire percent depth dose curve, all it relates to is the production of these electrons, or the ejection of these electrons from their shells. Now, despite this process of attenuation, photons, remember, they are massless packets of energy, so they can pretty much go straight through a body. So know that photons will always have an entrance dose when they exit the patient, and they will always have an exit dose as well. But just realize that it takes some time when photons hit tissue to reach that maximum activity, so they're not effective right at the surface of the skin. If we're applying them to bare skin, they're not going to be effective at the surface. It takes some time for them to get to that maximum dose. The other thing to realize is that the percent depth dose curve is different depending on the energy of a particular photon beam. So this table here just kind of shows what different photon beam curves might look like, ranging from 4 MV to 20 MV beam energies. The most important thing to realize is that higher energies will have a deeper depth of maximum dose. So the Dmax for a 20 MV beam will be deeper into the patient compared to that for a 4 MV beam or a 6 MV beam. So when you're treating with a lower energy beam, realize that your maximum dose is actually going to be closer to the periphery of the patient. I think it helps to see this kind of drawn out. So imagine what a dose distribution might look like if we use parallel opposed beams. So let's say we shine 2 beams, one from each side of a patient. Imagine that same percent depth dose curve that we just showed going from left to right is actually mirrored from right to left. So we have 2 Dmaxes, which are both on the periphery of the patient. And in the center of the patient, we're building up to that 100% dose. However, at the periphery of the patient, we actually have what is known as a hot spot, where the dose is actually higher than what we wanted it to be at the center. And that is, that's kind of unavoidable if we have just two parallel opposed beams, because we know that the way photons enter the patient, the Dmax is always at the periphery. And then, there's some attenuation that happens as the dose continues to move inward. I realize that this is kind of a lot to process right now, but I think the main thing you need to just understand is that when photons enter a patient's body, it takes some time before they reach that maximum dose, and then the beam continues to be attenuated. So if you're using simple 3D plans, such as parallel opposed fields, the hotspot will be at the periphery of the patient, closest to wherever your beam is entering the patient's body. There will be some buildup region as well, though, so you won't have maximum dose at the surface. So deep breath, we finally made it all the way through. I know that was a really long lecture, but hopefully now you have a better sense of the different types of interactions photons can undergo with matter, and also a better sense of how linear accelerators work, how photons are generated, and so on. If you don't understand everything in the very first review of this topic, it's completely understandable. It takes repetition. These concepts are difficult to grasp in the beginning, and then they come with time. So hopefully this was an enlightening introductory video for you. And I thank you so much for your time.